I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die.
Our speaker this evening is Dr. Franck Marchis, Senior Planetary Astronomer at the SETI Institute in Mountain View, and Chief Scientific Officer and co-founder at Unistellar. I have a disclaimer though. Both of tonight's organizational hosts, Tinka Ross and yours truly, are happy users of Unistellar's Enhanced Vision Citizen Scientist Telescope. So we may present Dr. Marchis with even more enthusiasm than normal because of our association through that equipment. Frank grew up in France. This explains why he may believe that I have such a pretty accent. Let's see, shortly after earning his PhD at the University of Toulouse, Dr. Marchis came to the US, but continued his work in solar system exploration at both the Observatoire de Paris and more recently at the Marseille Astrophysics Laboratory. For over 20 years and through nearly 400 scientific publications, Dr. Marchis has dedicated his life to the study of our solar system, particularly to the search for asteroids with moons, using telescopes with adaptive optics, which we'll learn about tonight. And Dr. Marchis's view is deep. He is currently part of the Gemini Planet Imager Exoplanet survey using advanced adaptive optics. Extreme, perhaps it's called, extreme adaptive optics. Back in 2007, Dr. Marchis discovered the first three-body asteroid system. Today, according to the International Astronomical Union, asteroid 6639 Marchis bears his name. Please give a warm cosmic welcome to the king of asteroid 6639, astrophysicist, Dr. Franck Marchis.
Thank you very much, Tucker. Thank you for having me. I see some familiar name in the audience today, so it's nice to see you not in person, virtually, but you know, I think it's we are going to be again together soon, watching the stars. So let's be a little bit more patient. So in the meantime, I'm going to talk about adaptive optics today, and I'm going to basically show how instrumentation has advanced so far that it's now possible for anybody to do scientific discoveries. While I was preparing this conversation, this presentation, I realized that I could not talk about everything, meaning all the topics that we study with adaptive optics. So I decided to focus mostly on the case of exoplanets. And if you have questions later on, I can describe some of the results we got, especially this week. We got some very exciting results with the study of Cleopatra, an asteroid in the main belt. But today, let's talk about essentially exoplanets. So my research is really motivated by answering this question, which is, are we alone? Are we alone in the universe? Is there any life over there? And to answer to this question, my role as an astronomer over the past 2 decades has been essentially to develop instruments, data processing system, so we can get direct information on the formation of the solar system and on the existence of exoplanet. So it's true that the universe is huge. Okay, we know that there is 3 trillion galaxies in our universe. So let's basically talk only about our Milky Way, our galaxy. And in this galaxy, there is still 250 billion stars. So this is a 3D representation of what will look like our galaxy if we drift far away from it and we're observing it back. So our galaxy is roughly 100,000 light years in diameter. We are located in this interesting area, which is called the Orion Arm, at basically 2/3 the distance from the center. We orbit around the galaxy in roughly 90 million years, around the center of the galaxy in 90 million years. Our sun is one of the stars of the galaxy. It's not that big, is not that small, is medium size. Our galaxy is also medium size, not too big, not too small, part of a cluster of galaxy in the Virgo cluster. So people often wonder, what's the link between your research and the SETI Institute? Why do you care? Why does the SETI Institute care that much about building instruments like telescopes and doing some research to study asteroid and exoplanet? Well, it's simply because to find life in our galaxy, we need to find probably planets first. And to find planets is great, but what we also need to do is to characterize them, to know what those planets are made of. There is various techniques to do that, but one of them, one of the most, I think, ambitious, and one of the one that will provide a definitive answer whether or not there is life in our galaxy by observing exoplanets, planets in orbit around other stars, is by simply imaging this planet, taking an image and analyzing this image, defining the color, etc. So that's one of the reasons a large portion of the SETI Institute researchers are, in fact, characterizing, searching for exoplanet. Is one of the, I think, the most promising way to find life in our galaxy. So, of course, if you observe the star with your naked eye, you will see at the best from San Francisco, I will say 24 stars. If you go far away up north, you will see probably, like, let's say in Sonoma County, you will see probably like thousands of stars. But that's not enough, okay? And what you see, you will see a tiny dot only. So to truly see details on the solar system bodies or see close to a star, you need to enhance human being. And how you enhance a human being is by using what we call telescopes. So telescopes was invented in 1608. The first telescope was built by a sailor. In fact, they were used by the in Holland to find us to see when boats was passing by, and an Italian researcher, Galileo Galilei, heard about this invention and basically built it himself in Italy, in Pisa, and used this telescope not to look at the boats or at his neighbors, but to look at the stars, at the heavens, as they call it at the time. And this telescope is basically this thing here. It was a very small telescope. I will say less than 5 centimeter diameter. I've seen a copy of it in Rome at the Vatican. And with this telescope, when Galileo Galilei pointed toward first the moon, he discovered that the moon is full of craters. He saw details that nobody else have seen before, because he enhanced basically the vision of human being. He gave us an access with this instrument to a better vision, a better view of the universe. He also reported the presence of the Galilean moon, Io, Europa, Ganymede, and Callisto, now named Galilean moon because of Galileo Galilei. He also reported the existence of phases on Venus and the presence of dark spot on the surface of the sun. So this invention is truly the beginning of observational astronomy. It's truly the moment where human beings were able to enhance their knowledge of the universe and record observations such as they see more than what human beings could have seen for millions of years. Of course, this telescope was not perfect. As I mentioned, it was a small size. It was full of aberrations. Without entering into much details, it's a refractor telescope, so we have this kind of chromatic aberrations, so the rainbows around each object. And we improve over time telescopes, and we now have significantly better telescope, and that's the story I'm going to talk about today. So, as I mentioned as well, we are not going to talk about all the science we can do with telescopes. And I'm going to focus essentially on those exoplanets, those planets in orbit around other stars. And let me tell you first why I think this is a very interesting topic of research. So the first exoplanet was discovered in 1995. That's a 51 peg. This planet was discovered at what we call radial velocity. So in this case, we don't see the planet. We see the motion of the star due to the presence of the planet. 51 peg is 51 peg B, sorry, the planet was the first planet. It was a planet that orbited around the star in a few days, very close to its star, and a gigantic planet, what we call now a hot Jupiter. So those are not the planets we see in our solar system. Between 1995 and 2010, basically, we used these radial velocity techniques to find more and more planets, and we discovered that indeed there is a lot of hot Jupiters in our galaxy. But then we launched in 2014, the Kepler Space Telescope. So this is a space telescope. It's a telescope designed specifically by NASA, and the PI is a NASA M, so locally here, to observe a tiny patch of the sky, the Kepler field of view. When I say tiny, is like 4 times or 10 times the size of the moon, but it's a huge patch of the sky. And they selected into this patch of the sky 120,000 stars roughly. And what they did with this telescope is to observe continuously this patch of the sky to see what they call, I have a problem with my presentation, so I hope it's gonna work. No. Sorry, I just need to find my pointer. I just lost it. Back. Here it is. They use this data to record continuously the flux of those stars. And what they notice is that there are some small attenuation for some of the stars passing at regular time, and those are in fact happening at regular time, and those are in fact the presence of a planet in orbit around the star. So in this case, and that's what you see in these figures, you don't see the planet, you see the shadow of the planet. And by measuring the shadow of the planet, the depth here, and knowing the size of the star, you get the size of the planet. And by observing this event multiple times, you get the orbit of the planet. So this is a very interesting mission because it revealed the presence of thousands of planets, in this field of view. Thousands of planets which are extremely different to the planet we see in our solar system. But more importantly, what astronomers did is to take this mission, and this was published I would say 8 months ago. So they took the entire result of this mission, the 4 years of observation of this patch of the sky, and they considered the population of stars they have, the number of planets they detected, etc. And they extrapolated this to the statistic of our entire galaxy. And this mission revealed that in average, in our galaxy, each stars have 2 planets. And more interestingly, among those planets, at least 300 million of them are potentially habitable. And what we mean by that is that they have a size which is roughly the size of Earth, and they are located in the habitable zone of the star, where you could have liquid water on the surface of the planet, if the planet has more or less the similar atmosphere than us. So this is an extraordinary number. 300 million planets, 300 million worlds that could be habitable, like our star, our Earth, our planet Earth. But as I said, I would like to emphasize that we say potentially habitable, because we are not certain that those planets have liquid water. We assume that because they located to the right place, the right position, and they have the right size, they could be like our planet. but we have not seen them. We have not seen those planets. We have not analyzed yet the light coming from this planet. So we have no certainties that those planets are truly like our Earth, with an ocean, a vegetation, a plate tectonic, volcano, animals, biosphere, and even like maybe intelligence. But that's the beginning of the search. And the motivation of my research now is that we know that those planets exist.
Does make any
Let's
difference.
try to take a picture of them. So this is the population of exoplanet that was discovered by the Kepler mission. Okay, so I mentioned the hot Jupiter, which are very close to the star, orbiting very fast, extremely hot. We have the lava world, which are the equivalent, but they are terrestrial, so they are same size than Earth, roughly. Then we have the rocky planets here, which are the planet we have in our solar system, but they are close to the star. They generally have a higher temperature. And then we have this weird, we have also the gas giant like Jupiter and Saturn. We have found a lot of them. And then we have this interesting population called ice giants, ocean world, super Earth, which are in fact planets bigger than in mass or in size than our Earth, but we don't really know what they truly are. We don't know if they are terrestrial or if they are purely gas giants like our Saturn or slightly smaller. So, but it's very interesting to see that we launched this mission to find exoplanet, to find the existence of exoplanet, and we found a lot of them. We know that there is exoplanets everywhere in our galaxy, but we also know that those exoplanets are not the same than we have in our own solar system. So it's very interesting because that means that if we study those planets and we get pictures in the future, we will learn a lot about the formation of solar system, and we will find out that our solar system is truly different than other solar systems or planetary systems. So how are we going to image those exoplanets? So my field of research always been to improve the image quality of telescopes. I was lucky enough to start working in astronomy in 1996. And at the time, that was the birth of the first adaptive optic system called ADONIS at the 3.6 meter telescope at ISO La Silla in Chile. And this drawing is basically a drawing of myself entering into the cage of the 3.6 meter telescopes to reboot the adaptive optic system, which was a prototype at the time. And I basically spent 2 years of my thesis doing this. So I'm letting you know this basically is the image that should be the front cover of my thesis instead of being the pretty research, the pretty picture we collected. Because I did spend a lot of my time on the top of this mountain, fixing this telescope, fixing this adaptive optics together with teams of researcher engineers at the summit. It was a prototype, it was working more or less. We had a lot of difficulties with the system because a lot of parts were coming from the military at the time. And of course, we didn't have a clear diagram or understanding of how they were working. But to summarize, adaptive optic system is a system that corrects in real time the effect of the atmosphere, atmospheric turbulences. It provides an image like if the telescope were in space. So when you have a 3.6 meter telescope with adaptive optic system, you do have a resolution which is extremely high, an angular resolution sufficient to see details on the surface of asteroids, on the surface of planets, for instance. We saw the rings of Uranus and Neptune using this adaptive optic system. We discover moons around the asteroid with this one. What's very important for those who want to know the equation is that the resolution is depending of the size of the primary, the factor D. The bigger is the telescope, the better is the resolution, and on the wavelength. So most adaptive optic systems in the 2000s were working in the near infrared for some technical reason that I'm not going to go through not today, but they were not providing a resolution better than Hubble Space Telescope because they were working in the near infrared at 2 microns. So we did have a resolution equivalent, I will say, to the Hubble Space Telescope using those 10 meter class telescopes. But then came this crazy idea of developing what we call extreme adaptive optic system. Extreme adaptive optic system, the goal was to basically have an adaptive optic system that will provide a perfect correction in the near infrared, allowing us to get correction as well in the visible light. So taking full advantage of the aperture size of the telescope. So to summarize, it will be like taking the 8-meter class telescope, a 10-meter class telescope, and getting images like if the telescope were in space. So we're starting this project in 2005. That was the first time we mentioned the extreme AO system. Bruce McIntosh is a PI of this project called the GPI, the Gemini Planet Imager. The Gemini Planet Imager, the Gemini telescope is in fact two telescopes, one in Chile and one in Hawaii. And this is a video of the sky of Chile taken from a mountain nearby, where you can see basically the Gemini telescope. So the design of this adaptive optic system was to provide the perfect correction. We use basically instruments that did not exist yet, deformable mirrors that correct in real time the atmospheric turbulences, and computer that did not exist in 2005. And it took us 7 years to build this adaptive optic system. So this Bruce McIntosh probably gave a talk already at Wonderfest, is a PI, is a professor now at Stanford University, and we still use the GPI telescope, the GPI instrument. So this is the Gemini Planet Imager, the Gemini telescope, sorry, in Chile. You can see it has this weird shape, like a spaceship. But inside, as you can see at the Casgrain, we have this instrument, and that's GPI. It's the size of a small car, basically. And inside this instrument, you have all this technology that I mentioned: deformable mirror, coronagraph that hide the image of the star so you can see the surrounding, and of course, computer that control this system in real time. The adaptive optic system run at 1,000 Hertz. So it means that we correct 1,000 times the shape of a deformable mirror, so we compensate for the atmospheric turbulences. And this is really the technology that boosted ground-based astronomy over the past 7 years. So this is a very emotional picture, I will say, because I was not there. I was in California at the time, but we are following the first light and the commissioning of the GPI instrument. Bruce McIntosh is here in the middle, the PI, and that's basically those smiles are the result of multiple nights and 10 years of development of the GPI instrument. And what you can see in the background here is the wavefront sensor that analyzed the image for the first time of a star in Chile. So this team is located in Chile, and this is the first image we collected, showing that the system was working almost as we planned. So we did this commissioning in 2014, 2015, we started the survey. The survey consisted in observing 600 stars, the brightest, the closest, the youngest of the southern hemisphere, to find exoplanets around them. GPI was designed for that. That was truly the goal of the instrument. We designed an adaptive optic system with all this technology, so can reach a contrast ratio of 1 million, meaning that we can see an object extremely close to the star, which is 1 million times fainter. And that could be a planet, for instance. But we found a lot of other things. In fact, what we found the most, which was surprised us, in fact, is the existence of a lot of what we call circumstellar disk. So here what you can see is it's a library of disk of formation, of planetary system information. The cross here is the location of a star, which you don't see because it's hidden by a coronagraph. But because of the adaptive optics system, you can see the surrounding of the star. And around the star, you can see dust grains and planetesimals, and those form those disks here. And they have different shapes because of the orientation of the system. They have gaps as well, you can see here or here, because there is probably here into this disk of gas and dust, some planets information. And those planets are carving through the disk by absorbing the material. We don't see the planet, but we see the effect of the planet into the circumstellar disk information. So here I'm showing you stars which are extremely young. We're talking about typically less than 20 million years old. Okay, our sun is 4.5 billion years old. So that's those are planetary system in their infancy. The stars just form. It's still surrounding by this dust and gas, and the planets are forming inside. And we can see the effect of those planets into the circumstellar disk. We learn a lot by studying those pictures about the formation of solar systems, of course, and planetary system in general. But then, finally, end of 2015, end of 2014, beginning of 2015, we get our first interesting result, which is the detection of Jupiter-sized, Jupiter-like exoplanet, which was the goal of the JPI instrument. You can see it here. This is a picture this is an animation where we scan through the wavelength. So this is the near infrared wavelength. So we scan through the different colors, and you can see here the planet. Of course, you can notice that there is a lot of weird features here, and you may ask me why you think this is a planet. Well, because we studied our instrument, we learn a lot about our instruments, and we have been able to understand that those are artifacts, and this is truly the planet. And what's really indicative of the fact that this is truly a planet is the fact that we can see the absorption band here of methane and water. So from this image, from this spectrum, we basically infer that what we're observing here is 51 Eridani b, a planet the size twice the mass of Jupiter, made of bands and belt, and with on the top of the atmosphere methane and water. Something very close to Jupiter, but more like a baby Jupiter. This is a 65 million years old planet, so it's extremely hot still. That's the reason we can see it so well, because we could see the heat coming from the planet as it's forming, as it's contracted. So this is the success story of JPI instrument. We build the instrument for that, and we discover this planet shortly after pointing the telescope and starting our survey. So those are other planets. This is another planet. You can see it's in this case it's Aegon, and you can see the planet moving. Here, this is 51 Eridani b. We observe it continuously for multiple years, and you can start seeing the motion of the planet and the orbit of the planet. So I think it's remarkable after, I will say, 20 years of discovery of the first exoplanet, that now we are capable of imaging some of them, taking a picture of some of them. And as I mentioned already, when you have a picture, it's not only seeing that you have here. We see the planet, we see the motion, we see the orbit, so we can do that quickly. But we can also analyze the color of the planet, and from the color of the planet, we get indication about the atmosphere of the planet, which is what we did for 51 Eridani b. So this is one of the greatest results of the JPI instrument. And I should mention that other instruments was created by other researchers to do this kind of analysis. In Europe, we have SPHERE, which also discover an handful number of exoplanets. And now we have another project called CARIS on the Subaru telescope, which is also able to image exoplanets, the type of the exoplanet the size of Jupiter, roughly. So to go back to GPI, we have imaged a few of those exoplanets. As you mentioned, I mentioned that we don't only take an image, we also have what we call a spectrum. So that's the spectrum of those exoplanets. But what I really want to show you here is that 51AWB is truly the most interesting one because it's the coolest in terms of the temperature. Okay, we talk about like 500 degrees Celsius here. So that's really something which is cold compared to the other planets we have here, which are very hot. So extremely young and extremely, probably significantly more massive than 51AWB. So we image those exoplanets, those young exoplanets, because they are easy to see. They're easier to see. When Jupiter cooled down, it basically is becoming less and less bright in the near infrared. So that's the reason, in fact, the planet we see the most are the youngest, because they are the brightest. So we have a bias in our survey, because we always target very young stars to make sure that we can find those those very young Jupiter. But despite this bias, one of the results we have is that there is not that many Jupiter-like exoplanets in our galaxy. And that's a problem. That was not something we were expecting. We were expecting to detect significantly more exoplanets like Jupiter using the GPI survey. And the issue arises for the other survey, for CARIS and also from SPHERE. There is something here missing, and we don't really know yet what, where we're suspecting that a Jupiter-sized exoplanet exists only if, meaning that it's not swallowed by the star or ejected by the star. So meaning that stay in a stable orbit far away from its star, only if there is a second exoplanet, the same size or the same mass. Like in our solar system, we have Saturn and Jupiter. This is a work in progress at the moment. There is still models being developed. But the point I want to make here is that this is a disappointment. It's a disappointment because we were not expecting to see an handful number of Jupiter-sized exoplanets with those instruments. We're expecting to see significantly more. Not 6, but I will say 50 or 100 of them. And we think that this is related to, one, the fact that probably they're significantly more rare than we expect. And two, there is something that we can improve in the instrument to make it more sensitive. And that's something we are working on at the moment with GPI. We are working on the GPI 2.0, which is a new version of GPI that will basically have a better sensitivity, we hope, and be able to see fainted stars, so fainter as well, Jupiters. So maybe detect more of those Jupiter exoplanet information. So this instrument will be is being currently is a work in progress, but the idea is to have it on the sky in Hawaii in the next 10 years. So we can wait for GPI 2.0, but we can also decide to use other techniques. So there is other techniques to detect Jupiter-sized exoplanet, of course, and one of them is a transit. So remember I mentioned Kepler that discovered a lot of exoplanets in this area of the sky, but we have launched other missions, and one of them is the TESS NASA mission that was launched 2 years ago, I will say, or 3. And TESS is basically a Kepler on steroid, meaning that it can observe, it can search for transiting exoplanets, and but it's targeting the stars which are closer to us, like magnitude 12 or 10, around 12 of 10, meaning that planets, planetary system which are 100 light years away from us. Okay. Kepler is observing things which are far away from us, like thousands light years away from us. With Kepler, we are going to basically look at the close environment of our sun, our neighborhood, and find Jupiter size and other exoplanets in orbit around those nearby stars. So TESS is running now. And this morning, when I was preparing this talk, I had this moment where I say, how many exoplanet tests we know and how many exoplanet TESS has discovered so far? So the number is roughly, for the number of exoplanet discovered so far, I think we are reaching almost 5,000. Meaning we have 5,000 exoplanets known in our galaxy at the moment. But if you look at TESS, TESS has observed 4,011 potential exoplanets. We call them TESS object of interest. So those are transit detected by the TESS instrument that could be exoplanet. And I will say roughly 80% of them will end up being exoplanets based on what we know so far with the instrument. So that's a lot of words, okay? That's a lot of potential exoplanets. So what's important is that TESS observe an area of the sky for like 20 days, roughly 27 days, then move to another area of the sky. And the data analysis is done, and then we discover planets in the first area of the sky. And sometimes we say, well, it would be great to observe it again, or at least to have a confirmation of the existence of this exoplanet. And that's where come new facilities. The idea here is to basically use smaller facilities connected with the TESS target of interest to confirm the existence of those exoplanets. And we're doing that now with TESS, but we have to be ready because there's going to be way more of this potential exoplanet coming soon with the KEOPS mission of ESA, the Plateau mission of ESA as well. Those missions going to deliver as even more exoplanet than the TESS mission because they're significantly more sensitive. So we will need a lot of validation from the ground, from other facilities to confirm the existence of these exoplanets. So options will be to build hundreds of thousands small telescopes and hire thousands of astronomers to do this work, or maybe robots. But another solution, which is what we envision, is to use the creativity and the energy of people who are willing to do astronomy for fun. And that's come from the Unistellar network. So Unistellar network is basically a network of small telescopes. It's a telescope that you can purchase right now. And it's a telescope that allows you to enjoy the dark sky, to observe galaxies, nebulae, comets, whatever you want. But you can also get from us alerts to observe, to participate to scientific investigation. This is the first exoplanet detected by a unistellar EV-scope. I forgot when it was done. That's amazing that I forgot that, but it was in April 2018, I think. And that's the target is HD 209458b, which is a very famous exoplanet because it's the first exoplanet detected by transit, in fact. And this is a Jupiter-sized exoplanet in orbit around a G-type star, a star like our sun. So you remember I say we want to be able to confirm the existence of Jupiter-sized exoplanet because we notice there is less of them than we expected. TESS will probably find a lot of them, but now with this tiny telescope, we can also confirm their existence. So you can be part of the scientific conversation here, doing truly scientific research that is cutting edge and extremely important for our understanding of the formation of the solar system. So the Unistellar EV-scope is a small telescope that you can, it's basically a 12-inch aperture telescope, Newtonian. It's a digital telescope. It's basically an integrated system. It's a robotic, smart telescope that can align itself, provide its, can give you the list of targets you can observe. The way we did this, it's basically by having a sensor at the prime focus of the telescope, a computer on board. So the photons come on the primary, reflect on the sensor. the data are being analyzed by the computer. So the computer will basically analyze the field of view and recognize where it's located, because he has millions of stars in this database to tell it where the telescope is pointing. You control it with a phone. So the telescope know all the time where you're located and have an accurate estimate of the time thanks to your phone. So when you have align the telescope, you can use the telescope to do any type of observation you want. And in the case of the EV scope, you can see the image here. So the image we capture, it's an image which is stacked and processed in real time. So we take short exposure, 4 seconds typically, and we basically modify the image. So we remove the rotation of the sky, remove some aberration introduced by the vibration of the telescope, but also by the atmospheric pollution, for instance. And then this image is combined and gets better over time. So in a few minutes, you can see a galaxy from San Francisco. The goal here is to make a system which is easy to use, so people truly enjoy using the telescope. The point is that I have one here behind me. If it were clear, I could do a demo remotely and be ready on the sky in less than 5 minutes. Right now it's not clear. I live in San Francisco, and the fog came this afternoon, so it's not going to be possible. But it's possible with this telescope to truly do observation quickly, and that's really the goal. It's not only Unistellar is not a company that designs telescopes. It's a company that wants to bring back astronomy to people, and also bring back at the same time the excitement of astronomy to everybody and discoveries. So to do that, we partner with the SETI Institute. So the SETI Institute is a scientific partner of Unistellar, meaning that we can, researchers at the SETI Institute, myself and Tom Esposito and others, we basically design scientific research around the network of the telescope. Scientific research could be observation of asteroid by occultation, observation of asteroid flybying Earth for planetary defense, exoplanet transits, supernovae, transient events, etc. So we use data coming from professional telescopes. So for instance, in the case of TESS, we have access to the TESS object of interest in real time. So Tom go every week through the target and select targets that could be observed by the telescope's network. Then we send notification to our users using, at the moment, emails and Slack, but soon we're going to be able to do that directly through the app. And those users can basically use the telescope if they're located in the right place at the right time to observe the transiting exoplanet. When they observe it, we have a method to observe it. I don't want to go to detail. We can talk about that later on, but they send us the data on our server at the SETI Institute, and we process the data. We can also send to the user the data if they want them to do their own data analysis, and we generate the Lie curve confirming or not the existence of this target object of interest. So this is the concept of the Unistellar network. Those citizens, this is a concept we had basically 3 years ago, and now it's a reality. I'm not going to go through all the results we get, but I'm going to show you a few of them. So in April, we have April last year, our first citizen astronomers, Julien de Lambilly, observed from Switzerland, Qatar 1b, which was a TOI at the time. And you can see, you can see here the Lie curve. So what you can see here is basically the attenuation of the flux of the star due to the presence of the shadow of a Jupiter-sized exoplanet. And this is done using this telescope from his backyard. So to give you an idea for those who do astronomy, we can observe with a single telescope stars with magnitude of less than 14. So typically what TESS observe as well, and transit depth of 1%, meaning that we can detect Jupiter-sized exoplanet around G-type star. In March last year, we did a calculation based on the current the library at the time of TESS, and we have more than 200 targets TOIs that could be observed with the Unistellar network. So that's a lot of targets, of course. And you need to be located at the right place at the right time to see this transit, because some of those transits happen only every 30 days, 100 days. So you need to be basically located in, it needs to be dark at the place where you're located to be able to do this observation. Our goal is to help NASA and ESA to confirm exoplanet, confirm the existence of the Jupiter-sized exoplanets in our case, refine their size, their orbit, and also study their close environment. Maybe we will see that those planets are binaries, for instance, so maybe they have rings. This is observable directly using transiting exoplanets. And interestingly as well, we can do what we call TTV analysis, timing analysis. So in this case, what we do, we look at the timing of the event. Like you can see here, this dashed line here is basically the center of the event. And you see some small perturbation of a multiple transits. This could be due to the existence of another exoplanet, sometimes a smaller one, like a super Earth in orbit around the star, that is perturbating the motion of the Jupiter-sized exoplanet. So I think it's exciting now that with this technology, citizen astronomers, people who have never done astronomy, Julien had never done astronomy, if I remember properly before. The first time he was using a telescope for science was with this EV scope. He basically confirmed an exoplanet. And you can do that now with this technology. And I'm not saying you can do that only with Unistellar. It's possible to do that with another telescopes if you are savvy enough to build your own technology, your own telescope. But since I'm here to talk about Unistellar, of course, I'm emphasizing the fact that in this case, we have designed a telescope which is easy to use. So everybody with a phone who can purchase this telescope could do this kind of research. So what concretely happened over the year? Well, during the year 2020, we shipped the first EV scope end of 2019, to give you an idea. So during the year 2020, 2021, the Unistellar network grew so much that I think I'm impressed every day I look at the map. We have now 5,000 telescopes distributed around the world, mostly in Europe, North America, and Japan. But we started 6 months ago to also distribute our telescope in Australia, New Zealand, and now we expanded the network in Asia, India, and Hong Kong, also in the Middle East and in South America. So the network is growing slowly but steadily, and those users, some of them become citizen astronomers. We have at the moment 500 roughly citizen astronomers in our Slack channel. They talk to us, they get information from us. They know when there is an occultation, a planetary defense program, and they talk to each other. So we're creating a community of citizen astronomers willing to do scientific campaign. We have 800 of them that joined scientific campaigns so far. And it's just specifically to talk about the Exoplanet program. Tom mentioned to me yesterday that we have 300 observations collected by citizen astronomers, 95 detections. So we have 100 roughly exoplanet, which has been confirmed using our network. And those detections come from 87 citizen scientists around the world. So every day when I see this new data coming and I see these new light curves of occultation, I think we have managed to basically make astronomy accessible to everybody. And I can see the excitement of people when they get the first light curve and they see that the contribution to the scientific research when they were observing from the backyard with our EV scope. So let me show you some of the ideas we have to improve the network, to show why the network is so important. So one thing we can do is to ask users to observe together the same transit. So we did that. Forgot the name of this star, it's gonna pop up after. But we have 3 users here who observe, that's the 3 colors here, a transit. So what you can do after processing them, you combine this data and you get an amazing light curve. This one is HD 189733b, which is also Jupiter-sized exoplanet in orbit around a G-type star or K-type star, I think in this case. So you can see the high quality of the light curve. So you see the high quality of the light curve, meaning that you see the transit exactly, but you also need, what interests us is not only the quality of the transit, is the timing as well. And because you have all these multiple points coming from different UVers, we can improve the timing to less than a minute in this case. So we have a very accurate estimate of when the transit is happening for this exoplanet. And we are doing this more and more now by combining multiple observations from multiple users around the world. This is a very interesting result that came out very recently, like from our users themselves. So Bruno in France, he lives in Normandy, noticed that there was this interesting transit of a target of interest here of number 2031-.01, if you want to know the details. So what he did, he contacted on our Slack and asked an American observer if he could observe at the same time, simultaneously, during the same night, I meant, the target. So Bruno got this part of the diagram here. That's his observation, his 3 or 4 hours of observation. And then Justice from, I think, Georgia, took over and observed the rest. And what you have here is a combined light curve made by 2 observers located 6,000 kilometers away from each other, who observe at the same night the same exoplanet to confirm the existence of this exoplanet. So that's the kind of data, that's the kind of observation we are able to do now with this community of citizen astronomers using this digital telescope. And I think this is unique. Something I should mention is that one of the main advantages of our technology is that those telescopes are identical. So the data processing is significantly easier for us. We know the detector, we know the telescope, we know the behavior of the telescope as well. So that's the reason we can combine so easily those observations and get such a good result. Okay, amigo, let me just mention briefly the future and leave I have 5 minutes to finish this. So I just want to discuss a bit about where we are going now in the field of astronomy to image exoplanets. The goal, the true grail of any astronomer who studies exoplanet is to be able to one day get a picture of another pale blue dot, another Earth-like exoplanet, a planet like Earth with water, continents, biosphere, etc. To do this, we have to invent to test new technology. We cannot do this with the current telescopes. In this case, an Earth-like exoplanet is 10 billion times fainter than its star. So it's a very difficult challenge, of course. We have to get a much significantly better instrument. So one solution is to go to space. So here is the Hubble Space Telescope, 20 or 30 years old now. But what NASA is envisioning is to design a new generation of telescopes which are going to be significantly bigger in size and have a significantly better instrumentation. All of them, and that's a main point here, will have adaptive optic system in space. So this is the LUVOIR telescope. It's a concept telescope, but it's possible to do a telescope of this size now. It's a 11-meter size telescope aperture, protected by the shield here to provide extreme stability. And as I mentioned, with an adaptive optic system. This telescope will be able to image, based on models we have so far, 380 Earth-like exoplanets. So we will be able to see exoplanets and analyze and get information about those exoplanets using this kind of telescope. But this is not going to come now. This we're talking about 2040, and there is multiple other projects in competition, such as the ABEX here. And personally, I'm not sure I'm going to wait to be retired to be able to get a picture of an Earth-like exoplanet. So one solution, and I want to finish with that, is to to think smaller but faster. Instead of building a telescope, space telescope like LUVOIR, let's focus on the very close environment of our solar in our galaxy. Let's focus on the closer stars, like for instance the Alpha Centauri system, made of 2 G-type stars, 7 billion years old, that orbit around the center of mass in 80 years. It's possible that around these stars we do have Earth-like exoplanets, planet like Earth. And since those stars are extremely close to us, only 4.2 light years away from us, it will be easier to detect these Earth-like exoplanets. So let's design instruments specifically for that. So one idea is to use the next generation of telescopes. You remember I mentioned that we have 10-meter class telescope now. Well, we are thinking about the next one, the giants, the ELTs. And this is one of them. This is the European Extremely Large Telescopes. It's going to be a telescope of the size of 40 meters. The size changed recently, so I need to always recalibrate it. But that's basically the size of the primary mirror. It will collect enough photons with this primary mirror to be able to see the Earth-like planet like Earth. But it will be also equipped with adaptive optic system. And because it's so big, this adaptive optic system will have what we call a laser guide stars. So we will create in the sky faint stars that will be used as a reference point to get the best image quality for this adaptive optic system. And this is not science fiction. Europe is building this. They already started the construction. First slide maybe in 10 years, we will see. But I think those are the systems that will probably provide the first image of an Earth-like exoplanets. And I just want to show the end of the video because I think it's extremely cool to see the lasers. When you will go to Mauna Kea or when you will go to Chile to see those gigantic telescopes, you will see in the top of them those bright lasers. They will be used to create those faint stars to get the best image quality. But those telescopes, as this is a simulation, will be able to image Alpha Centauri A and B. And what we did here, we use a design of an instrument that we call Tiki to show that if there is around Alpha Centauri A, in this case, an Earth-like exoplanet, we will be able to detect it using this telescope in the mid-infrared, in another wavelength. And this is interesting because with this wavelength range, you'll be able to differentiate between a planet like Venus, extremely hot, or a planet like Mars, very cold. Because in the mid-infrared, we see the color, the temperature of the planet itself. I would just finish that by saying that those are grandiose projects, but we do have smaller ideas. We have the idea of a small telescopes like Project Blue, the size of a fridge, with a 30 centimeter telescope mirror. And in this case, this telescope, also equipped with adaptive optic system, will observe continuously for thousands of hours Alpha Centauri A and then Alpha Centauri B. And from our simulation, we show that it will be possible to see with this technology a planet like Earth around those stars, especially in this case, invisible. And that's the reason the image is slightly blue here, is because here, this is Earth basically seen from using Project Blue in orbit around an Alpha Centauri star. So we see the color of the ocean. So I will end here by saying that, let me skip this, that we do make progress in astronomy. Progress in astronomy with adaptive optics. Now we have the ambition of building telescopes and adaptive optic system that will be one day able to detect an Earth-like exoplanet, to collect an image of an Earth-like exoplanet, and probably find life, if there is life over there. Microbiological life will be detectable as well. I'm not talking about civilization and cities here, but simply a biosphere has a significant impact on the atmosphere of its planet. So if one day we detect an Earth-like exoplanet and we are able to analyze the atmosphere of this planet, we will see the signature of this biology happening. Of course, there is still the possibility that we are not alone and there is other intelligence over there. And this intelligence will be also detectable by those instruments. And to go back to the Unistellar project, the ambition of this project is truly to create a community of researchers, citizen astronomers that will participate to the scientific conversation. Because this project is bigger than astronomy. I mean, finding life elsewhere, it's something bigger than what I can do myself alone in my shed today. We need to have everybody involved to be able to do this research. So having these thousands of small telescopes, BCV scope, and maybe another type of telescopes in the future, will help to find these exoplanets and characterize them and understand, and finally maybe find out whether or not we are alone in our galaxy. Thank you very much.
Wow, thank you, Franck. Thank you, Dr. Marchis. As you can see, the chat is full of good questions here. I just want to remind people that if you're nervous about asking me to read your question for you, please use the reactions button at the bottom of the Zoom window and raise your hand, wait to be acknowledged, please, then make yourself visible, or certainly at least turn on your microphone, and you can ask the question yourself. All right, so Franck, would you like to be able to call you Franck or Dr. Marchis?
Franck is fine.
Franck, great, okay. Well, I'll go in order here. Jack asks, is the field of view of Kepler fixed, or can it be changed to view different parts of the cosmos?
The field of view of Kepler mission was fixed, but then when Kepler had an issue with his wheel, he started drifting, basically. So they found a way to make that Kepler observe the ecliptic, and that's not called Kepler anymore. The mission is called K2, the Kepler 2, basically. And with this mission, they also detected exoplanets. But in this case, they basically observe different stars over time as the telescope is drifting due to the solar wind. They are published, I think it was this week, the last catalog of the K2 mission. And frankly, this week has been busy for me. I didn't even look at the result yet, but it's coming.
I feel guilty that we slowed you down and that data.
Oh, it's good. It's good. You can wait. Don't worry.
Dave asks, in your slide entitled Exoplanet Populations, with the graph of planet size versus orbital period, what is the area in the lower right corner called? Why is it called frontier?
Because that's basically what we cannot observe yet. That's the goal. I should have mentioned that, because that's the goal. We want to be able to find planets here, because those planets, remember, Earth is 365 days and 1 AU, so it should be here. Yeah, we want to be able to detect planet here, because those planets probably are Earth-like exoplanets, meaning that they orbit around their star in the habitable zone. And they are, and they're small enough to be kind of like our Earth.
So your explanation there just essentially answered my question as well, regarding that one dot on this display that is nearest the frontier, has an Earth-like size and an Earth-like period. Yeah, so statistically, it's not unusual. That's the limits of our observational ability.
That's correct. That's the limit of our observability, and we're improving this. TESS is going to be able to theoretically to go further here, based on the result we have. But the problem of TESS is the fact that TESS observe every 27 days one area of the sky and move. So you need, if you want to see it Earth twice, you have to be timing exactly the motion so you can see the planet, the second transit of the planet. But there is some planet in the celestial northern pole, some star in the celestial northern pole and southern pole that can be observed for a very long period of time, for more than 300 days. So we are going to see those long period planet coming from TESS in the next year, probably. It's coming.
Great. Hugh, no, excuse me. Yes, Hugh Cayley asks, are the Chilean and Hawaiian telescopes connected in some way?
No, the Gemini observatories are made of two telescopes. They are not connected, meaning that they don't exchange data. It's not like a radio telescope. The reason we have two of them is because it's cheaper to build two identical telescopes, and being able to observe the northern sky and the southern sky is very important for astronomers. What they also do, since the telescopes are kind of identical, they exchange instruments. So that's the reason GPI, it was at the southern Gemini, and now it's going to go to the northern one.
All right. Thank you, Frank. Stuart Y. in Cupertino asks, he's got a preface here to the question, Earth has had a relatively calm recent history, about 10,000 to 100,000 years of calm, with regard to the stable geology and also stable weather. This has presented an environment which I believe, says Stuart, has fostered our human progress to develop our civilizations and collective intelligence. Here comes the question. Can you imagine any way for your telescope system to remotely determine which planets are in a similar quiet or calm period, conducive even perhaps to human visits and potential colonization, that is, ideal Goldilocks planets?
That's an entire talk all by itself, but that's a very interesting question. So there is two things to consider here. One is the sun, the star of a system, is also a problem. Some stars are known to be quiet. G-type star are the perfect example. That's what we hear. If you're on an M dwarf star, I would say I'm not a star specialist, but I think every 1,000 years they have this kind of super hard burst, and that can sterilize the entire surface of the planet, especially if the planet is close. So for us, that's one of the reasons it's important to look for a G-type star to find life, because if you want to find life like our on the surface, we need to find life around the G-type star roughly. So we have a stable environment. Then for the planet itself into the solar system, the planetary system, an important factor here, and that's something I didn't say when I showed this slide, that we do know that to have water on Earth, so in the inner part of the solar system, we had to find a mechanism to bring this water from the outer part to the inner part. Water did not, there is still debate. I'm not gonna say that like that, but there is a huge debate of the origin of the water on our planet. And it seems that the water of our planet, it's not coming from our planet itself. It has been brought from far away to us, from the outer part of the main belt to us. And this mechanism, one scenario is what we call the NIS model, is an interaction 3.7 billion years ago between Jupiter and Saturn that destabilized a disk of planetesimal of icy material in the outer part of the solar system, sending water in the inner part of the solar system. So contaminating our terrestrial planet with the water from the icy world. So that means, and that's the reason it's mentioned that here, that if you want to have a planet with water, if the scenario is correct, we need to have at least two Jupiter-sized exoplanets in the planetary system. So we do have this destabilization, so we have an ocean world like our planet. I don't know if I was clear enough, but what I meant is that we need to have two Jupiters to be able to bring the water from the outer part to the inner part, based on this NIS scenario. And that's one of the problem we have. So we have by finding only one Jupiter in planetary system. It's very possible that in fact all the terrestrial planets in these planetary systems are extremely dry, so they will not have water. And in this case, they will not have life like our. And then for the stability, started to study. And personally, I'm not a geologist, so I don't know much more about climate. But if you look at the scale at the evolution of the climate over the past 2 million years, it's true that our climate has been relatively stable. But if you look on the scale of 1 million years, 800 million years, our atmosphere changed radically. We have this great oxygenation event, for instance, that brought oxygen into our atmosphere and killed 90% of the planet on the surface of 90% of the species on the surface of the planet because of that, because oxygen is a poison for most species. And so that's something we are starting learning by studying our own planet. And I don't think we are yet ready to do that for exoplanets, but when we will have a LUVOIR telescope or something, or the ELT, my dream will be that we will be observing a lot of exoplanets like Earth at different age. And maybe we will finally understand the evolution of those terrestrial worlds at the scale over time. And that's something we cannot do yet. But in the future we will, because something important to mention is that stars have different age. Some stars are extremely young, 10 million years old, and some stars are very significantly older than our sun. So imagine that we see terrestrial planets around each of those stars, and we study them. We will know how those exoplanet atmosphere evolve over time, and if our evolution is significant or is very peculiar in the scale of the galaxy. That was a long answer. I'm sorry.
Wow, thank you, Frank. Hugh Cayley asks, do you think the circumstellar disks are matter that is becoming planetary bodies?
Yes, we do know that, in fact. We do know that there will become planetary bodies, most of us. There is a very interesting picture taken by the ALMA millimeter array, which shows some of these disks. We call it the cocoon of planetary system. And inside, you can see how the planet which is forming is basically carving into the planetary system. And there is an announcement recently made where they see as well a kind of an exomoon, a planet in formation, and they see the cocoon around the planet, and they think that this is a Jupiter-sized exoplanet in formation with the moons, the exomoons as well. This was announced 3 weeks ago. So we're talking about something very new here. But we are witnessing now in some of those disks the formation of planets and the moons.
Thank you, Frank. Dave has asked quite a few questions here. I'll try to be fair to others and ask maybe just one or two. How big a telescope would we need to be able to actually image a rocky planet like Earth around a nearby star?
How big should be a telescope to image a planet like Earth around a nearby star? So based on the analysis we made for Project Blue, a 30-centimeter telescope observing continuously Alpha Centauri A or Alpha Centauri B, I'm talking about 4,000 hours, will be able to...
Frank, did you say 30 centimeter?
30 centimeter, yes.
Okay. Yes, okay.
Because in space, the goal here, if you have a small telescope, what you need to collect photons coming from the planet, right? So the way you can do that is by observing continuously, and you get millions of photons from the star, and there will be one photon coming from the planet every 2 hours. So now imagine you observe for like 10,000 hours, or every minute, I would say. You observe 10,000 hours, so you get more photons coming from the planet. Okay. So that's the technique we're using with Project Blue. It's exactly that. We have a small telescope. You go to space, stable environment, no atmosphere. We have an adaptive optic system on board the telescope that's stabilized for the variation of temperatures and the optics, which are not perfect. And we observe continuously for 4,000, 10,000. And that's the image we got. That's a simulation, of course, of Alpha Centauri A And here, this is Mars, this is Earth, and this is Venus, if I remember properly. So we could see an Earth-like exoplanet with that. If you observe from the ground, you need to have a bigger telescope because you cannot stay in a very stable environment. There is the atmosphere. There is the fact that you cannot observe because of the rotation of Earth for 4,000 hours continuously. So in this case, you build a 30, 40 meter class telescope like the ELT. And in this case, you will be able to see the planet like we see here in the mid-infrared.
Great. Thanks, Frank. Jack asks, is the data from citizen telescopes released as open source for others to analyze?
The data released to the users. That's the deal we have with them. Okay. So if you observe, if you have an EV scope and you observe with your EV scope, we send you the data. We don't send them to the community at large at the moment. That's something we could consider. And it's not something we're against it. It's just a question of a priority right now. Right now, the priority is to make sure that every citizen astronomer who has observed, can have access to his data, of course. And that's a work in progress. But as soon as this is done, I'm totally willing to think about having a system which basically release the data to a broader community. But that's something we need to find a platform for that. I have some ideas, but we're not yet ready for that.
All right. Dave asks, what are the pulsar timing and microlensing, two different methods of finding exoplanets?
Yes, so those I didn't mention them because I wanted to talk about optical only. The pulsar timing is definitely not optical, it's radio. So in this case, it's a perturbation. The pulsar is the remain of a massive star. It's kind of a lighthouse, but it's bright in radio. Okay, so we project every second, so every 2 seconds, a very bright pulse that if we align with this field of view, we receive like a lighthouse. Planets, if there is planets in orbit around it, these planets are basically kind of perturbating this lighthouse, this pulsar. So we have some small perturbation in the signal. So that's the first technique, it's radio. We discover the first exoplanet really was discovered using this technique. It was I forgot the name of the pulsar, it's a bunch of numbers, and it's radio astronomy, so it's not really my field. Then we can talk about microlensing. So that's a very interesting technique as well. And that's something that we will do probably with W first in the future. In this case, what we see is the enhance of the brightness of the star in the background as the planet is passing. And this enhancement is due to deformation of the space continuum, basically. And this is measurable, basically. But it's an event that happened once, meaning that you need to be exactly aligned and see the planet to see the planet signal. But then you will never see it again. It's a great technique to provide information on the size and mass of planets, but you will never be able to go back over there and to analyze it again, meaning that you will see the planet once and that's all. So it's a technique that's going to be used by W first. We changed the name to the Grace Roman Space Telescope. Is going to survey, this telescope is going to survey with this large field of view a large area of the sky, and there is team that's going to basically analyze continuously the brightness of the stars to detect for planets by microlensing. And it will provide statistical analysis of the number of exoplanets because we detect the mass in this case. So we will know how the percentage of planet, Earth mass exoplanet, Jupiter mass exoplanet, etc. in the future, thanks to this technique.
Great, thank you, Frank. Boy, what a good evening.